So please welcome Eric Jang.
Thank you. Thanks. Is there a clicker? Oh, this one. Cool. Hi, everyone. My name is Eric Jang. I'm a research engineer on the Google Brain robotics team, also known as Robotics at Google. So deep learning is a really exciting narrative for robotics because it's imbued robots with unprecedented levels of perception and the ability to handle open-ended, unstructured environments. It's a big part of what I work on at Google. But in this talk, I want to actually share a perspective that is a little bit more kind of unusual, which is that not only can deep learning do a lot for robotics, but robotics has a big opportunity to help deep learning a lot. So in the last few years, there's been a lot of successes applying deep learning-based methods for robotics. I'm just going to talk about one of them, but there are many. In this work, we call it QT-opt. We use a deep neural network to learn how to grasp objects from a bin using only a RGB image. And the way we do this is that we have the robot pick up objects randomly from the bin, and if it succeeds, we give it a reward of 1. If it doesn't, we give it a reward of 0. And just by using reinforcement learning and trial and error and a lot of robots, we can get these robots to pick up any object from the bin with a lot of reliability. We want to make robots generally useful, and one way to extend grasping capabilities is to pick up a specific user-commanded object. For instance, there's a comb in this bin, and we want the robot to pick up the comb. So one way we can encode objects is like ImageNet-style labels. So the comb is just a big vector of zeros, and the index corresponding to comb is set as 1. But this presents a lot of challenges in RL in the real world because we need to find a way to assign rewards if it picked up the right object, and this requires general perception. So how do we tell the robot whether it picked up the comb or not? In previous work, we used this idea that a robot can actually interact with the world to make the labeling problem simpler. When it picks up an object that we don't know what it is, we can actually use the robot to bring it close to the robot's camera and obtain a easy-to-classify picture of the comb. So then, by using some semi-supervised learning, we can retroactively assign the label of the cropped image back to the bin. And we use this to kind of supervise what it picked up. So this theme of using the robot to make the learning problem simpler is going to be a big part of this talk. And so we extend the grasping model in prior work to not only predict the probability that it picks up any object, but also the probability of the correct object class. And this is work we did in end-to-end learning of semantic grasping. And so on the right, you can see this figure where we have a plot of the object that we asked the robot to pick up and the class that it ended up picking up. And we had like 16 object classes. So one of the goals of our research lab is to actually get out of the research lab and make robots useful in the real world. On the left, you have the kind of idealized kitchen scenario where there's a single microwave, a single ceiling light, dishwasher, sink, and so forth. It's very similar to what you would see in like a segmentation or object detection data set. On the right is a real-life home setting. Objects are much more cluttered. There's a lot of doodads whose object identities are ambiguous, and it's generally very hard for robotic perception to understand the huge diversity of objects that we would see in the real world. So I don't think that class-based recognition is going to cut it. If you look at the class distribution of ImageNet images, there's a very long tail of objects that are just generally rarely encountered, but a human might ask a robot to pick up anyway. The most common classes are actually Yorkshire Terriers. Also, human-assigned semantics are really tricky. Consider this image here. Are these bowls or cups? I don't know. Like, it depends a lot on the context. And I would even argue that the act of assigning a label to your data imposes a lot of structure that can actually make the robotic learning problem harder. So in our previous semantic grasping work, what we found was that there's a bunch of objects for which you would assign the same semantic label, like toy or comb or brush or something, but they can be extremely visually distinct. And in some sense, we don't actually care whether the robot understands what a human calls an object. We just wanted to pick it up. So in this follow-up work, we consider the problem of instance grasping, where you show the robot a picture of the object you want, or maybe instead of a picture, you tell it what you want or just have have some kind of dense vector representation of a particular object, and it has to pick it up. And this is a much more specific way to tell a robot what to do than just a one-hot vector, which we use for class-based conditioning. But we still have the problem of how do we get robots to understand objects? The labeling problem becomes even harder because we're now matching objects at the instance level. So I want to take a step back and actually ask the question broadly, how do we teach deep learning models anything about the world in the first place? The recipe is actually very simple. First, you gather data about the world. And then the second step is that you fit a model to assumptions you have about the world. So what do I mean by this? Well, in the supervised learning, the setup is actually pretty contrived and trivial. You gather a large data set of images, and you ask humans to assign a label to each image. And then the assumption you make about the learning problem is that the label can be extracted from the image. Things get more interesting in unsupervised learning. For instance, let's say you have a video. The assumption we make here is that the video, there's a lot of temporal structure in video that we can potentially leverage for unsupervised learning. So in one of my favorite works from 2018, this paper by Karl Vondrek and colleagues, the assumption they make about the data is that the pixel color in a single frame can be derived by indexing into the last 5 frames of the video, because objects don't really change between subsequent frames. And if you force a model to learn these assumptions, it actually learns, what emerges from this model is this unsupervised object tracking behavior. So we're going to use a similar idea, but what's different about our work is that we actually use a robot to impose the structure we want to see in the data into the world. And I want to argue that the act of intervening in the world using a robot can create a lot of nice structure that leads to powerful unsupervised learning. The assumption that we make in our work, which we call grasp to vec, is that it's very simple. If you have a set of objects and you grasp one of the objects, the assumption we make is that the set of objects before the grasp minus the object is equal to the set of objects after the grasp. Concretely, on the left, you have a bin of objects before you make a grasp. Then you pick up an object and you look at it, just like we did in the class-based semantic grasping work. And then after the grasp, the object's missing from the image. So we want to enforce the idea that an embedding of the object before the grasp minus the object is equal to an embedding of the scene after the grasp. It's very similar to this idea in word to vec, where there's also this kind of emergent structure where, like, if you subtract Italy from Rome and you add France, you get Paris. And so deep learning methods seem to be able to extract these kind of compositionality. How we train this thing is we take these 3 images, we pass them through convolutional neural nets. We have these spatial feature maps that represent like the kind of encoded image features. We then collapse their spatial dimension by just pooling across the height and width. And so we get these dense vector embeddings that represent sets of objects. Then we use a contrastive loss called n pairs to basically enforce that the top 2 embedding differences equals to the embedding of the object itself. And so when we train this thing, we get some very interesting properties that emerge from this. The first is that we can use these networks as a recognition model and tell whether 2 objects are the same or not. Notice that this can recognize objects even when the cup is rotated or potentially occluded by the gripper. The second property that emerges is that we can use this to localize objects within the scene. So if you have this goal object of a sprinkler head, which is kind of like you're looking at it from the bottom, the network can actually figure out in the grasping image where the target object is, even though it's in a completely different pose. And on the right, you see this attention heat map that is plotting as a function of spatial distance. Here's another example. So on the right, you have the goal image, which is this deformable mesh bag thing. And the scene is kind of occluded by this tape dispenser, but it's still able to figure out where the object is in the scene. And this kind of object detection and identification was all done without the use of any labeling whatsoever. No labels were gathered in this experiment. Here's a video. Can we play the video somehow? Thanks. So we take these 2 pieces of the model, this detection and similarity model, and we combine it with our previous Qt-opt grasping work, which can pick up objects from a bin, to realize an instance grasping policy where we move the object to the localization target, and then we just run Qt-opt, the indiscriminate thing, and it just learns to pick up objects that we ask for. So on the left, you have the goal image, and on the right, you have an outcome, and the similarity is what the model thinks how similar the two objects are. OK. Next slide. So this is a very simple baseline that just combines an indiscriminate grasping policy with a kind of approach target that's used with our localization and similarity models. So we get 80% on objects that it's been trained on, and then it generalizes to, well, it generalizes a lot better than 62%, but when we combine it with the actual grasping policy, the performance goes down a little bit. And we have some ideas on how to improve this. But overall, we're able to do instance grasping pretty well without telling the robot whether it succeeded at picking the right object or not, just by using these kind of unsupervised losses. So the hot take I want you all to leave with is that I think the biggest wins in representation learning don't necessarily come from better modeling ideas, but really thinking about how you can create better structured data. And when you have robots, what you can do is use interventions to create the structure you want to see in the data, and then when you do representation learning on it, it can give your robots even better intervention skills. And so you have this virtuous cycle of robots generating labels for representation learning and representation learning generating labels back for reinforcement learning in the real world. Finally, I want to thank my colleagues and many others at Google and X Robotics. And I'm happy to take any questions now.